Welcome back, everyone. Today, I'd like to get a start on chapter 22, at least getting us through the first two sections. Doesn't sound like a whole lot to do, but the reason I want to sort of bide my time here, not rush through these two sections, is because in my experience, the whole disentanglement of keto and enol forms of carbonyl compounds and the enolate ions that we can derive from carbonyl compounds with at least one alpha proton. In my experience, that's not the easiest thing to get straight. So first thing we need to do is remind ourselves about carbonyl compounds that have at least one alpha proton. We call such carbonyl compounds enolizable. And again, this can be any carbonyl-containing compound, ester, ketone, aldehyde, you name it, as long as it has at least one alpha proton. If there are no alpha protons, game over. None of that apply. None of what we're going to say applies to such compounds because they are not enolizable. But carbonyl compounds with at least one alpha proton are normally written this way in what we call the keto form, but there also exists a special kind of isomer of the keto form. That special kind of isomer is known as a tautomer, and this other isomer is the enol form. Now, these two species are in equilibrium with one another in protic solvents. And ordinarily, the keto form is very much preferred. So ordinarily, the equilibrium, as I've written it here, lies very far to the left. But there is a mobile equilibrium between these two species. And depending on what else is attached here, there will be some percentage of the enol form in solution as well. The only cases where the enol forms are significantly more stable and begin to get up towards an equal amount as to the keto form, maybe even more than the keto form in solution, is those compounds that have two carbonyl groups in a 1,3 position relative to each other. So 1,3 dicarbonyl compounds. And I think you can see why that is. If you look at the enol form of 2,4-pentane dione, for instance, you can see that there's a couple things going on here. First of all, the carbon-carbon double bond in the enol form is now conjugated to the other carbonyl group. And incidentally, there's an additional enol form, right? It's equivalent to this one, but it would have had the carbon-carbon double bond here and the carbonyl still here. But in either case, you've got a conjugated system. And as you recall from, I believe, chapter 10, conjugated double bonds are more stable than isolated double bonds. And the other thing going on here is that you have hydrogen bonding between the OH group of the enol, of the enol OH. Well, you have hydrogen bonding between the hydrogen of the enol OH and the carbonyl oxygen on the other side. Not only that, you can see it forms a quasi six-membered ring. So that's a very stabilized species. Apart from that, generally the keto form is favored. It's only in these cases like this, and we'll be looking at compounds of this type later on. They can do some special chemistry just of their own because of the special stability of their enols. So much for keto forms. Any carbonyl compound that has at least one alpha hydrogen will also exist in its enol form. And this is an equilibrium. So there's a rapid equilibrium, again, normally favoring the keto form, but with some percentage of the enol form present as well. Unfortunately, the enolate ion, which is the conjugate base of either of these, the enolate ion is a resonance stabilized species, and that's the tricky part. We have to deal with both of these types of arrows, both the resonance type arrow, both the equilibrium type arrow and the resonance type arrow. But all enolate ions, regardless of the carbonyl compound that they're derived from. So again, I'm leaving all of these bonds that you see here, can be to anything. This can be any kind of derivative whatsoever. any kind of carbonyl compound in the enolate. The enolate thereof is going to be a resonance stabilized species, which means that there is just one structure, right? This is not an equilibrium over here. There's no flipping back and forth involved. Remember also that when we discuss resonance stabilized species and look for resonance contributors, remember we're not allowed to move any atoms. We have to leave all of the nuclei in the same place. And what we're really talking about here is one single structure that is at all times a mixture, a hybrid of these two structures. What that means is that the negative charge is partly in the carbon atom and partly on the oxygen atom. And that's true, again, of any enolate ion. And I suppose if I asked you all to make a wild guess, take a stab as to which of the two atoms bears more of the minus charge, you would probably all correctly guess that it's the oxygen that bears more of the minus charge. That being said, as you'll see when we start to get into the chemistry of enolates, it's actually the carbon that reacts usually. And that's because you get stronger bonds to carbon than you do to oxygen. And so you get more stable compounds that way, more stable products. So the overall picture, if I really wanted to consider all of it, here's our enolate ion over here. There will be an equilibrium between the keto form, whoops, that was not what I intended, an equilibrium between the keto form and the enolate ion. In other words, going from the keto form to the enolate involves removing the proton, namely that proton. So any sufficiently strong base can do that, and we'll discuss later on what sorts of bases tend to do that for us. So in this direction, we're losing a proton, and in this direction, we're putting the proton back on. In fact, we're putting it back on onto the carbon. Meanwhile, let's cheat by doing something like this. There's also an equilibrium between the enolate ion and the enol form. And so going in this direction from the enolate to the enol form involves putting a proton on the oxygen. And so then you get your enol form. And going in the other direction involves pulling the proton off the oxygen. And again, there are bases that will do that for us. And we'll eventually talk about what are those bases that you will need to know. We'll use them in reactions. But I would say something like this is really what the whole picture looks like. In the middle, you've got a resonance stabilized species. That means whenever you're drawing an enolate ion as an intermediate, and it will show up as an intermediate in a lot of reactions that we're going to cover over the next couple of chapters. But whenever you're drawing an enolate ion, it does not matter which of these resonance forms you draw. Either one of them can be used to draw a correct mechanism. And that just highlights that there's one species here. Unfortunately, our usual method of drawing molecules using the valence bond model falls apart here. And so we can't really draw the one single structure of the enolate ion terribly easily. We have to go with one of these resonance contributors. And so if the enolate ion is protonated on the oxygen, you get the enol. And if the enolate ion is protonated in the carbon, you get the keto form. So that's really the entire scheme. But that is why I wanted to take some time to dwell on this, because in my opinion, this is a little bit tricky, that you have a situation that involves both equilibrium and resonance. So now's a good time to get those two things really very well distinguished in your head. And we'll talk about the reactivity, or if you will, the instability of enols later in the next section. But there's a good reason why enols are so much less stable than keto forms ordinarily, other things being equal. And the main reason, as we'll go over some examples of this in just a moment, but the main reason is that the presence of this electron-rich oxygen atom makes the carbon-carbon double bond here very much more electron-rich. So it's electron donating by resonance. And so the reactivity of this carbon-carbon double bond is very much greater than what it would be if the OH group weren't here. In other words, if you just had a standard alkene. And we already know, we'll bring this up as I said again in a moment, we already know from chapter 7 and 8 that alkenes like to react with electrophiles. Well, enols all the more so, because it makes the carbon-carbon double bond that much more electron rich and therefore that much more susceptible to reaction with electrophiles. So as I said, we'll get to some examples of that shortly. One other thing we need to point out before we get onto those examples is that keto-enol tautomerization can be either acid or base catalyzed. What that means is that the process by which we change a keto form into an enol form or an enol form into a keto form can be done in aqueous acid or in aqueous base. Both ways work. We just need to be sure that, first of all, we always look at what we're given, so we make sure that our mechanisms make sense. And then after looking at what we're given, we're careful to show only species and intermediates that make sense. Remember, in acidic solution, we don't want to see any strongly basic anions, right? No hydroxide, no alkoxides, no carbanions, no NH2-, nothing like that. About the furthest we can push it in acidic medium in terms of anions is maybe carboxylate ions, the conjugate bases of carboxylic acids. That's about the limit. Beyond that, we're probably pushing it too far. The only other anions that we can imagine as being present in acidic solution are the conjugate bases of strong acids, so chloride, bromide, iodide, bisulfate ion, HSO4, that's the conjugate base of acetic acid. Anything between that and maybe acetate ion, that's about the limit. Anything much more basic than that can't exist in acidic solution in any reasonable concentration. And likewise, when we consider alkaline solution, we need to remember that we don't want to see any cations. The only cations that can live in alkaline solution are metal cations, Na+, K+, Ca2+. Those are fine. Anyway, we're not going to use those in our mechanisms, right? Those are always going to be spectator ions. So, but certainly no carbocations, no oxonium ions, meaning no oxygens with a plus charge, nothing like that can exist in an alkaline solution. And so you need to be able to tell which is the case based on what you're given. And so here, of course, we're given H3O+. Pretty obvious, I think, that we're in acidic solution. And so if one were to go from the keto form to the enol form, tautomerize in this direction in an acidic solution, well, of course, we would use a hydronium ion to put the proton onto the carbonyl oxygen, as you see over here. And again, I'm not using the hydronium ion here because I've memorized that it goes there. I notice that that, in fact, is what I'm given, right? That's what's over the arrow. I've got hydronium. That means the things I have present, besides the organic species, are hydronium ions and water. So those are the only two species I can use. But not every acidic medium is an aqueous solution, right? We've seen examples where you can have an acid catalyzed process in an alcohol or in an amine. And then we don't use H3O+, right? We have to think what the conjugate base of the solvent is going to be. But here we're totally fine using a hydronium ion because that's what we've got. That's what we're given as being present in the solution. So now we've got this cation, and now we need to convert that to the enol form. And that's done. Oh, by the way, I should mention, I'm using cyclohexanone here just as an example. I could have picked any carbonyl compound that has at least one alpha proton. And of course, cyclohexanone is 4. So anyway, once we form this cation, we'll use our water molecule, that's the most alkaline species we've got around, to pull off any one of those 4 equivalent alpha protons. And we'll use the electrons in the carbon-hydrogen bond to form a carbon-carbon pi bond. And then we will break the carbon-oxygen pi bond, thus getting rid of the plus charge in oxygen, and then we've got our enol. And these steps are reversible, by the way. You can just use the exact same mechanism with everything exactly backwards. All of the all of the electron flow going in the opposite direction to go from the enol form to the keto form. But that's how it would look in acidic solution. In alkaline solution, however, now we would presumably have some source of the hydroxide ion, at least in an aqueous solution. So we will use that, and you'll notice I'm not even drawing the Na, right? It doesn't do anything. It's a spectator ion. So one of the things I've meant to say after the last couple exams is if you're using Na plus or K plus or something like that in a mechanism, you are definitely doing it wrong. I can't think of a single place where you will need to show an alkali metal cation, because it's the hydroxide ion that's doing the work here. That's what's got the extra electron density. Anyway, that will pull off again any one of those 4 equivalent alpha protons. We'll use the electron pair in the carbon-hydrogen bond to form a carbon-carbon pi bond, and we will break the carbon-oxygen pi bond. And in so doing, we're now putting a minus charge in oxygen. That's completely okay in alkaline solution. And so in order to complete the process in this direction, we simply protonate that oxygen using now a water molecule. That's the most acidic species we've got around, and that will give us our enol form. And again, if we needed to show it going in the opposite direction, both of those steps are reversible. You would simply follow the whole thing in the reverse direction, just flow the electrons in the reverse direction. Really, I should have used equilibrium arrows on all of these. These are all reversible steps. So all that being said, before we get into sort of hardcore into the actual reactions of enols and enolates, I want to talk a little bit about alpha substitution processes in general. That's what this chapter is about. And so, if you'll recall about enols and enolates, enols themselves, of course, are resonance stabilized species too. And normally we will draw them like this. It's normally kind of a pain to draw them like that, but it would not be wrong. So it's not just enolates. Enols themselves are resonance stabilized species. And as you can see, the other resonance form, which I think we would all conclude is the minor contributor, right? Because we've got 2 atoms with charges on them, whereas in the other resonance form, there's no charge on any atom. But there is some amount of this other resonance form in the overall molecular orbital picture of the species, and it shows that there is a little bit of extra electron density on that carbon atom. And so, as we said earlier, let me just put up a quick alkene over here. We'll get rid of the OH group. And again, I'm not even specifying what's on those other bonds. It could be anything. But we already are well familiar with alkenes reacting with electrophiles. We had 1 or 2 whole chapters on that. That was back in chapter 7 and 8. And then really actually chapter 9 also. That was alkynes instead of alkenes. But we know that alkenes can attack electrophiles. We saw many, many reactions of that type. And in so doing, we'll in general get a carbocation intermediate that then needs to be attacked by a nucleophile. But if you compare an unstabilized alkene of this type to an enol, and again, you can look at it, you can look at the idea using either of these resonance forms. One could look at this resonance form of the enol and show the oxygen atom helping out by helping to push out the electrons in the carbon-carbon pi bond to attack the electrophile. That's one way of looking at it. Or it would be perfectly reasonable to show this carbon atom, this carbanion carbon, as it would now be, looking at the other resonance form, just attacking that electrophile directly. Either way, you will now get a species that, unlike in the case with unstabilized alkenes, unlike in the chapter 8 reactions, you'll get a stable adduct, a relatively stable adduct that does not have a carbocation. All we have is an oxonium ion. And so whereas in chapter 8, in general, we needed some nucleophile after attack of the electrophile, or attack onto the electrophile of the alkene. In general, we then needed some nucleophile to attack over here. In the case of an enol, we don't need that. All we need is even a moderately decent base to be around and simply pull the proton off the oxygen. And again, it doesn't matter which way you draw the mechanism. You get to the same place either way. I would encourage you to work that out, draw the structures, and convince yourselves of that. But that is why enols are so unstable. Again, you could read unstable as reactive. Enols are very reactive as nucleophiles, and they react readily with electrophiles, even more so than plain old unstabilized alkenes can do. And so that's really the main point that I was making over here. So that, I think, is a good start in chapter 22. We'll stop there for now. I feel just with that, I've given you something to think about. So we'll pick up in the next section later on. I'll plan on getting all of the rest of chapter 22 put up here to YouTube, certainly by sometime next Tuesday. So other than that, have a great day, and we'll see you later.